Hi, my name is Dane Wagner. I'm a senior hardware engineer at National Instruments, and I'm on the digital Phosphor implementation for VirtualBench on our VB8034 product. I'm going to talk a little bit about digital Phosphor, what it is in the industry, and how National Instruments is accomplishing this feature using some Xilinx hardware. So, we've got a capture here. The signal is doing a few different interesting things. The idea here is that we're doing an acquisition every time the screen updates. So we're doing really 20 to 30 acquisitions per second. Now, if we're looking for this signal to do something odd, let's say it only does it one every 10,000 times. We'll be sitting here watching the screen for a really long time before we actually see the interesting thing that we're looking for. Digital Phosphor improves on this by acquiring as fast as the hardware physically can and rendering all of that information onto a single frame, which is then delivered to the user. You probably have all seen digital Phosphor in the industry. It's on most mid and high range scopes. But this is our first digital Phosphor implementation at National Instruments, and it's all thanks to Xilinx hardware. So we have this signal here. It's hard to kind of tell what's going on with it. So let's enable digital Phosphor. This is the default mode, so I've intentionally turned it off just to show you the difference between the two. Immediately, we can see there's a lot more records, there's a lot more information here. Digital Phosphor uses intensity information to indicate how often a particular signal passes through a particular ADC code, for instance. So you can see some interesting behavior here. There's some crosstalk here that you can see is correlated. This is a clock line. The yellow is a data line. You can see there's some crosstalk between the two. It's very easy at a glance to see what's going on here compared to what we had with sample mode. You would have to, like I said, sit for quite a long time to see all of the different artifacts and all the different behavior that you're seeing on the signal now with sample mode. So inside the VirtualBench, we're doing all of this rendering to some dedicated RAM from acquisition memory. That rendering is all done in the hardware. I mentioned we want to acquire as often as possible. We want to capture those unusual events and display them as quickly to the user as possible to reduce debugging time. So all of that rendering and acquisition is done in the hardware. So that's implemented with some custom VHDL that I personally wrote. And
where does it live?
It lives in a Kintex 7. There's a Kintex 7 that controls the scope, does all of the DMA. The Kintex 7 is mostly the digital Phosphor rendering engine, a little bit of logic for controlling and configuring the ADCs, and the memory interface generator talking to some dedicated DDR3, along with a bunch of our custom DMA circuitry to move data around. So the way digital Phosphor works is it retrieves the acquisition buffer out of RAM, and then it performs some interpolation on it. We have to do the interpolation before we render, because once you render a series of ADC codes, you lose all correlation information about it. So while it's very useful for displaying to the user, there's a lot of interesting information lost when we actually do that rendering. So we have to do the interpolation before we render. The interpolation is done, it's a 16x interpolation. We use an FIR filter. So we have, I believe the filter depth is about 6 or 8 taps. So we're doing a lot of multiplies, and we generate these intermediate ADC codes. Once we have that, you can kind of imagine within a frame buffer, you have a starting point and an ending point, and you want to draw a line between the two. To do that, we pull some clever tricks in the digital logic. We actually use a 256-bit add, and we use the carry chain to propagate the status that you're between these 2 points. And we break that apart into 228-bit adds just to pipeline it. And we didn't have to spend much time optimizing that circuitry because the carry chain in the Kintex 7 is so fast that it just worked. It met timing. It hasn't really been problematic. It's really been a joy to work with. We came up with the idea and we put it in the hardware, and it just worked. So that was really cool. Working with a MIG has also been really useful. We didn't have to design any of the DDR3 interface. It pretty much just worked out of the box. We got some custom DMA stuff in there, so we've got some wrappers around it, but the ease of use really let me focus on the cool algorithms to actually do the rendering, to figure out the right interpolation to use to make our data look good. And the Kintex 7 really enabled this feature. We wouldn't have been able to do it without it. So that's Digital Phosphor at National Instruments, our first implementation, and we hope you like it.
Thanks.